Thank you.
How can we go any longer without a little tune time?
Right, okay, thank you.
Yeah.
Thanks very much for that. Okay, I don't mean to suggest that physics is an error, not at all. All the physics that's generally accepted is good. I mean to say that there's a fundamentally erroneous ways of thinking which prevent us from getting further than we should. I mean, for example, there's an awful lot of papers being produced on particle physics, endless ones, and these make categorical statements about physical truth, which are often highly questionable. There's an awful lot of rubbish produced as really high quality professional work, and it isn't. It's not physics, it's interpretation that's to blame.
Speculation.
Yes, speculation, but the interpretation is garbage, very often. And what I think this is shows the problem with our physics education, which is in many ways very formulaic. It doesn't teach people to conceptualise and think, it teaches them to shut up and calculate. And I think this has led to the present impasse, where we've not done anything new since 1973 at the fundamental level. Conceptual thinking is treated as though it's trivial or irrelevant, when in fact it's the core of physics and the basis of everything good that we've ever done. Now, just at this moment, there are lots of people producing hundreds of papers which we know to be wrong. We know that they're wrong, and the reason we know that they're wrong from experimental evidence, even before the papers are written. Because a lot of these authors, and these papers generate a lot of respect, they're in big departments, they're churning them out and publishing them in big quality journals like Physical Review Letters and all that sort of stuff. And the problem is that experimental evidence has shown that they can't possibly be true. And yet, it's like, as I say, it's like pursuing industry when it's been outmoded by something else. They're still tooled up for the old industry, so they're still producing it.
There's too much reward for it.
There is. So, how do we know they're wrong? Well, many people are developing a standard model of particle physics by thinking you can tweak it to produce some simple addition to the particle hierarchy. You can get higher Z and W, you can get supersymmetry, you can get multiple Higgs bosons and all that, which will explain all the anomalies. But the problem is, we know it's impossible, because the Large Hadron Collider, having discovered the Higgs boson, has already shown, I think they've discovered it, yeah. But even, whether they have or not, I'm sure they have, but what's happened is that they can actually now work out all the couplings between the Higgs and all the other particles, and they've measured quite a few. And those measurements determine what other particles can exist. And we already know that higher mass particles cannot exist unless they couple even more strongly with the Higgs. And we would have seen it already. And we don't see it, and so we know that these particles can't exist at all. And yet they're still producing loads of papers on it. Now, concerning the Higgs mechanism, I found a site which left me completely incensed when I read it. It was called Of Particular Significance, Conservations About Science, with theoretical physicist Matt Strasser. Anybody know? It has a feature on why the Higgs and gravity were unrelated. Now, what I found particularly objectionable about this site wasn't what it said, it was the tone. It was we professionals, believe in this, and amateurs might think that, but real, proper physicists don't think that. And it was really quite appalling. And here we read, there's no connection between the Higgs mechanism and gravity. That idea is completely wrong. Gravity isn't related to mass, but a combination of energy and momentum. Here, mass is assumed to be rest mass, presumably. Gravitational forces don't obey Newton's law based on mass, quote, but Einstein's based on energy and momentum. And though these particles owe the mass to the Higgs, the neutron and the proton don't. and certainly not Higgs itself. Well, let me just put up the standard model particles. Now all these are the fundamental quarks, these 6. These are the fundamental leptons, and these are the gauge bosons that cause the interactions, the strong interaction, the electric interaction, the weak interaction. There on the right is the Higgs boson. And they say that all those particles, their masses are determined by the Higgs. We know that. But that one on the right isn't. Okay, so they're the basic particles and they're all determined by the Higgs. But this is the proton, 2 ups and a down. This is three quarks, coloured quarks, with interactions mediated by gluons. And what they say is this does not owe its mass to Higgs. This owes its mass to these interactions. This dynamic energy of the gluons give it its mass. That's what they say. And this has nothing to do with the Higgs interaction. And they say that categorically. And these masses are big. And this is most of the bulk mass of objects in the universe is made of these. So this has nothing to do with Higgs. So according to the author, the Higgs field isn't universal. Because though the Higgs field interacts with the electric and weak, it doesn't interact with the strong between quarks. Because we've just shown that. I'm not going to bother about black holes. That's irrelevant to my discussion. Now, what is particularly striking about this kind of argument is that it doesn't actually recognise its own limitations. It doesn't say, as far as we know, or we've got problems with this, but the best thinking is so far. It doesn't say that. It's categorically we know. It doesn't recognise its formulaic and superficial assumptions, and some of which are actually known to be speculative, and some are merely alternative. They're not necessarily correct. Yet, it's written with this air of professional authority, as though we'd solved all the deepest problems in physics and weren't floundering, as I say, weren't floundering about with an idea where to turn to next, which is where we are. So it's written as though we've solved everything, and we're not actually in a mess. No, we're in a mess. It's no idea of its own limitations. If you think you've got all the right ideas, even though there's lots of things you can't explain, you make it impossible to go beyond that. And this is a ridiculous and preposterous attitude, but it's very, very common, because it makes people feel as though they're important.
Like infallibility.
Yeah. It's the professional status. We the experts, we theoreticians know how to do all this. You idiots can't do any calculations.
Unzicker is saying what is driving it is the funding, not just the profession.
The funding as well, I agree with you entirely. Funding goes into all this.
It channels the funding.
You're absolutely right, Tom. Absolutely right. Now, what I'm going to show is that every one of those claims is wrong, or at least might be wrong. There's not one of those claims is actually definitely true, and I think some are definitely wrong. And here we'll begin with the problem of mass. And somehow, in the last 20 or 30 years, the concept of mass has come to mean only one type of mass. That is the rest mass, the fixed mass, the invariant mass. But there's no such thing as invariant mass. It's a non-concept. So Einstein's special theory of relativity introduces a lot of new features into dynamics. Lorentz transformations, the gamma factor. So the particles at high speed behave very differently from the way people thought up to about 1880. But if you define rest mass as or invariant mass, the mass as that, and insist that you can only use the word in that context, you make it impossible to connect supposedly classical dynamics with Einstein's dynamics, or post-Einstein dynamics. And this is against Einstein's own practice, because he wanted smooth connections with classical physics. So he wanted a transition between the two. We don't have any problem in understanding that transition and the whole context if we say that any dynamics pre or post-relativistic, if we define all dynamics according to their relativistic meanings. We do that. And then it means the dynamic laws remain valid. We have the conservation of energy, the conservation of momentum, the conservation of mass, the conservation of angular momentum, all those remain valid. If we do that, we can define force and other concepts in that way. And to me, it's more important to preserve the laws of physics than a definition of a concept which was never made. Nobody ever defined that mass in that way before, because the concept didn't exist. And I say, if we stick to early definitions, supposedly, it's like we're saying we can't use a modern version of the idea of a chemical element because that's not how Lavoisier used it. Lavoisier's idea of a chemical element was very different from ours, so therefore we can't use the word element. It's like saying that. Physics concepts have always been evolutionary. It's the laws that have remained constant to a large extent. And one of the evolved concepts is mass. That now includes momentum and energy. That's what we understand, and we call it relativistic mass. If we talk about any previous definition, the only one I can think of is Newton's quantity of matter, which doesn't mean anything at all. Doesn't mean anything special. It's just another name for mass. It doesn't correspond to what we call rest mass, certainly. But in any case, rest mass is an absurd concept. It's completely wrong. There's no body and no object has ever been observed with its rest mass. Every object has had a dynamical mass, only some of which was its rest mass.
Quite.
Yes, quite, yeah. And in addition to that, all mass anyway is dynamic in origin, as we'll see. There's no mass due to a state of rest whatsoever. They talk about protons and neutrons having a dynamic mass due to the gluons. And that's practically all the rest mass in the universe is due to protons and neutrons, which have a dynamic origin due to the gluons. And that's their argument. So, if objects of matter look solid, most of it's coming from the dynamic energy of gluon exchange. And the quark masses, if you try to measure a quark mass, you can't really fix it at all, because it varies in the energy. There's no fixed value for it. It's clearly dynamic. But even the most invariant of invariant masses, like the mass of the electron, is dynamic as well, because the mass of the electron is from the subtle motion known as Zeta-Bewegung, which is an oscillation of the particle between our space and the vacuum. It's a dynamic mass in the first place. It's determined by frequency of oscillation, the Compton frequency in effect. So it's not rest mass at all. If you talk about rest mass and invariant mass, it's just a special case of mass. And it's like saying, oh, from now on, all of time has got to be what we call proper time. We can't accept any other concept of time. Rubbish. And even Newton, who was the originator of the modern concept of mass, didn't see it as an idea fixed in stone. In his work on optics, by the way, yesterday I published the first of 3 books on Newton, which the other 2 will come out shortly.
Yeah. That's quite.
And this one is called Newton and Modern Physics. I'll say a little bit more about Newton later. In his work on optics, he's actually exploring dynamic mass. He knew that mass wasn't a fixed thing. He knew that there was something funny about it when it came to photons, as we would call them, or light particles. And that's a very interesting story. I'll tell it sometime, but not today. So if we adopt the evolved concept of mass, there's no reason why we can't use Newton's law of gravitational force and the conservation of energy, momentum and angular momentum. No problem. So let's look at the Higgs mechanism now. Is it true that the W and Z bosons, the gauge bosons, the quarks and the leptons are the masses to Higgs, but neutrons and protons don't? And here again, we know that the composite structures of quarks, the standard statement on this is it's not due to the Higgs mechanism at all. It's completely due to gluon exchange. But I'm going to show that's wrong. And they say they can't get the proton mass from quarks because the quarks aren't heavy enough. That's true. It doesn't come from quarks, but it comes from the Higgs mechanism nonetheless. They say it's from the gluon exchange. It's true. It is from the gluon exchange. But the gluon exchange is created by the Higgs mechanism, as I will show. And it can only be done in the nilpotent formalism, which shows one of the powers of that formalism. See, gluons are massless in this sense of rest mass. So they're like photons. So how can something massless produce something heavy, like a proton, solid and heavy? That is a puzzle. Nobody's explained that. And in fact, there's a big prize for solving it, the mass gap problem. The Clay Institute has offered millions of dollars for solving that. By the way, if anybody wants to nominate me, you can't nominate yourself. Now, if we don't have an answer to the problem, I say it's presumptuous to the point of hubris to assume that it cannot be due to the Higgs mechanism. And yet that's what's done by these people. Well, I will show that it can. The characteristic signature of the Higgs mechanism is all about handedness. This is the spin of the particle, that the particle's moving that way, right-handed spin, left-handed spin. The standard theory of the weak interaction tells us that only left-handed fermions, that's basic particles, and right-handed antifermions interact weakly. Left-handed antifermions and right-handed fermions don't. So if you have a typical fermion, for example an electron, it'll have a two-component wave function, superposition of two states, one of which is left-handed, one of which is right-handed. Only the left-handed part interacts weakly. So how do we know that it's got a right-handed component? And the answer is because it's got mass. Particles with mass must have a right-handed component. How do we know that? Well, there's a nice heuristic argument that if you got a massless electron, it would travel at the speed of light, and you couldn't overtake it. So if it was left-handed, it would always be left-handed. You would never see it right-handed. But if it had a mass, you could overtake it, look back, and say, oh yes, it's right-handed. And so that's how we know that a particle with right-handedness must have mass. And the amount of mass is measured by the fraction of right-handedness, or the other way around. So the tau, which is the lepton below the heaviest lepton, is more right-handed than the muon, which is the middle one, which is more right-handed than the electron, which is the lightest. Now let's look at the nilpotent wave function. Nobody before has ever written down a wave function, a real wave function for a three-component particle like a proton or neutron. Now, if this is a typical nilpotent wave function, I'll explain why there's both plus and minus there afterwards. If we were doing it properly, we would have 4 states, but I'm just writing the first one for convenience. But if I write that down like that, with 3 states, the answer is 0, because it's nilpotent. It squares to 0, so if I multiply those 3's together, I get nothing. So that can't be the way we would write it. However, there is a way we can write it, like that. Because we know that the momentum term, the one that does the spin and so forth, is a vector. So it's got 3 components. And we can arbitrarily choose 3 components. We can call them X, Y, Z, it doesn't matter what directions. You can remodel this and do various versions of it, but basically it boils down to this. And this can be shown to be nilpotent, a proper wave function, when it's one of 6 possible states. When all the momentum is in X, either plus or minus, or all the momentum is in Y, either plus or minus, and all the momentum is in Z, plus or minus. So let me show you what that would look like. So I get rid of the momentum when it's, see that's all in X, so there's none there, there's none there. And if you look on the right hand side, you see RGB, RBG and so forth. These are the coloured quark combinations. And this is the symmetry of the strong interaction. And you can see this has the same symmetry, the SU3 symmetry, the famous SU3 symmetry of the coloured quarks. Now, there are two possible spin states there, the plus and the minus, and there's a reason for that. If I multiply these out, this is just a purely algebraic multiplication. When I multiply these out, this one reduces to this times a scalar value which can be, you can normalise it away. This one reduces to this one. So all that multiplies out to just a scalar number which can multiply by that. And so the final versions that we get are something like that. But the key thing here is that the middle two, these two, originally that was a plus py and it's now become minus. That was a minus, it's now become plus. If I go back to the original ones, you can see that was originally plus. But if you multiply them both on either side, you get minus there. This one here, if you multiply them on either side, you get plus. But these don't change. So in other words, if I want to retain the symmetry of that, I have to include the minus as well as the plus. If I only included one of the signs, then I would have an asymmetry between the three components. And of course that's not going to happen, because this is one of the famous threenesses, the rotation symmetry of momentum and space and so forth. So this one is switch sign, this one is switch sign, but to preserve the symmetry I have to have both signs, and that's why I wrote them down with both signs. Now, the way you interpret this in terms of handedness is that this one here, that ratio, when you get a plus ratio, well, we can say is left-handed. So this one here, when you get a minus ratio, is right-handed. So we have equal numbers of left-handed and right-handed. And now we know that equal numbers of left-handed and right-handed produce mass. So what we're doing now is showing that, I'm mentioning here about the switching the signs. So there has to be a maximal superposition of left and right-handed components. And the reason there's been an observed zero chirality, there's no special preference for it in the strong interaction. There's no preference for the right or left-handed. So now we know that there's a strong interaction simply by shifting those components around must produce a mass. Simply by the symmetry, which explains how important symmetry is. And I'm explaining that we get exactly the same structure as we do in the conventional strong interaction, and you can just do the calculations in the same way as you would. And if you want to write the gluons down, that's what the gluons would look like. So I can do gluons to exchange the spins will look like that. But contrary to this overconfident claims, when there was no full picture, they only had a half picture or a partial picture, and yet they were confident that it was due to something that was not the Higgs mechanism. However, from the perspective of this particular representation, which I know must be true, you get exactly the right answers from it. If you do all the calculations, you get perfect answers. It provides mass for the neutron and proton and all other matter of that kind by the Higgs mechanism, at the same time as directing it through a process of gluon exchange. So that claim of theirs is utterly and totally wrong. And in addition, the claim that the Higgs field was not universal was made on the basis that it only applied to 2 of the 3 gauge interactions. It didn't apply to the strong, it applied to the electric and weak. But no, it applies to the strong as well. So that claim is wrong as well. And the claim that there's no connection with gravity, you can bet that that's going to be falsified as well. So does it connect with gravity? Does the mass of the Higgs boson derive from the Higgs mechanism? Well, let's consider the boson, the Higgs boson. Now, at ANPA in August 2011, and this is before any indication of a discovery of a Higgs, and I worked with people who were working on it, and the first indication was in December 2011, that there was anything there. They didn't prove it till the following year, but they got the first indications then. I made a prediction that the mass would be of order 123. Now, how on earth could I possibly know that? Well, this is for a very specific reason, that the Higgs boson mass should be generated by the Higgs mechanism, like everything else. And it's actually the spin zero nature, which the author of our article thought was proof against, that is actually proof for. This is the very mechanism that even allows us to have spin zero at all. Let's look at a spin zero particle. We can't have this, because if there's no, we can't have a massless spin zero, because if there's no mass there, then this is the same as if you reversed all the signs, so it would be identical to that. And that combination would be zero. You see, to get a slim boson, you need a fermion and an anti-fermion combination. Now, there was a thing called the Goldstone boson, which is a preliminary to the Higgs mechanism, which was zero and which had to go. The theory couldn't maintain it. And in the Higgs mechanism, that Goldstone boson becomes massive. So if you create a massless one, that can't happen. So you've got to put mass in it. And that is the Higgs mechanism. A left-handed fermion cannot combine with a left-handed antifermion. They can't both be left-handed, only one of them can be left-handed. Because if both are left-handed, then we don't have a, we get zero. So in a nilpotent formula, the spin boson structure must have a mass, so I put the mass term in. And it must be either like that, or it must be like that. But we've got a left-handed fermion and a left-handed antifermion, or right-handed fermion and a right-handed antifermion. In both cases, there's something wrong. One's allowed, one's forbidden. However, it's not forbidden if we add mass. We can now imagine that the mass is accommodated to create is created to accommodate the forbidden component. And so let's take the vacuum and take half of it for one mechanism and half of it for the other, as we would expect, since we're taking half is the correct value, half is the incorrect, which will give us the value 123, because the Higgs vacuum is 246. Now, this is what I wrote earlier. The maximum energy required for either its fermion or its antifermion component to have the wrong-handedness and so produce the spin combination, zero combination. So the experimental discovery of the Higgs is 125 GeV. I was very close. And the reason for the slight discrepancy is something that's well recognised, that there's a small self-coupling of the Higgs, which even the most conventional theorists accept as a small part of the Higgs mechanism. And that does make that slight difference. And it will be the same for the electroweak bosons. Okay, so is the Higgs connected to gravity? Well, the Higgs field is absolutely continuous. Does it tell us anything about gravity? It's absolutely continuous. What does that mean? It means the energy density of the universe must be infinite, which is exactly the starting point for Big Bang theories. Not that I'm a great supporter of them, but that's where they start from. And I've always thought that means that really what it's telling us is that space is actually full of this energy at exactly that value, so there's no such thing as a movement of mass energy from one place to another. That's an illusion. It's not the energy that moves, it's the different manifestations of it that move. Rest mass, charge, stuff like that, different types of energy. And you can imagine that these manifestations move like waves do in a medium. Like the water doesn't move when waves move through it, just the wave. And it's something like that. No elementary particle, in my view, you will never get one that's as high as 246 GeV. Because you can't create more energy at a point than that. And I don't think you can get it higher than 246 over root 2, which is the coupling on the basis of quantum field theory. And that is 174 GeV, which is the heaviest particle we know, which is the top quark. It's very curious, this. Very interesting, but curious. There's no ordinary mechanical movement of charges or fermions at velocity v. This is what Zitterbewegung tells us. Charges only move at c. It's an oscillating c, but it's only at c. And c isn't really a proper velocity at all. There's no such thing as ordinary mechanical velocity. And I think it's curious that one of Newton's models of gravity has mass and ether as virtually, he's tried many models, mass and ether is mutually exclusive. So higher density means lower density ether and vice versa. Lower density ether means high gravity. It's a bit like, you know, what we get in Higgs. A bit like. Now I say that the reason why there must be a continuous mass distribution, it's required by, and Lou mentioned this group, the Klein-4 group. The Klein-4 group symmetry of space-time, mass and charge, which Mark also alluded to. This continuity says why mass is never negative and why mass at absolute rest is never observed. It's an immobility of the mass energy can be related to the extraordinary fact, almost it's extraordinary, that classical physics tells us the centre of mass of any system never moves. So there must be an infinite numbers of centres of mass that never move. Has anybody ever really worked out how that works? You know, if the centre of mass of any system never moves, you have an explosion, everything explodes out, but the centre of mass stays the same. There must be an infinite number of those at different points in space. It seems to be glossed over. Well, this is the Klein-4 symmetry, and it's this business here which tells us that mass is continuous, same as time. And that symmetry, to my knowledge, is a perfect one. We were talking about representations of mathematical things, and I have three well-known representations, artistic representations of that symmetry. And anybody who wants to can discuss those with me after. But continuous mass distributions are generic in physics. We have the zero-point energy, the cosmic microwave background radiation, even ordinary fields. Now that must make a difference to how we understand gravity. Perhaps we're getting something wrong with our understanding of gravity. Not the mathematical structure, but our understanding of what it is. We clearly don't truly understand it anyway. The static gravitational field is continuous. It's transmitted instantly. We know that. And we know that because it wouldn't fit in with special relativity if it wasn't. It's a remarkable fact.
Are you saying general relativity is wrong?
No. I'm saying the interpretation leaves something to be desired. I'm not saying the equation's wrong. I'll tell you more about general relativity later. Okay. The gravitational field isn't propagated. That's standard. That's not me. That's standard. It's only recently become accepted that that must be the case. But if you look up the Wikipedia article on that, you'll find that's what it says. I looked it up especially because I was very interested in that. The gravitational field isn't propagated. So, if it's not propagated, do we not have a mechanism for non-locality? Because we've got instantaneous correlation. And I'm very interested in the concept, I'm one of the originators in my view, of gravity gauge theory correspondence. Like gravity is the opposite side to gauge theory in some way. Gauge theory is the other three forces. So when I say gauge theory, I mean electric, strong and weak. All that stuff on one side, gravity on the other. They're kind of a cancellation. Gravity is the non-local bit to the three local gauge interactions. So many people, including the author of the website, just just blithely accept that gravity has a spin 2 particle, just as the other ones have spin 1, that's got spin 2. But once you get down to spin 2 particles, you get into incredible trouble, because you cannot renormalize your theory. It will not renormalize. It just creates infinities. Nobody's ever succeeded in renormalizing spin 2. But why do we assume that gravity must be a local gauge theory? Why couldn't it be the vacuum or non-local side of the quantized gauge theories? If you've got quantum theory, you've got two aspects. You've got local gauge theory and you've got vacuum. And you can't have quantum mechanics without both. You can't have a quantum theory without both. You've got to have the local and the non-local. They've got to exist at the same time. It's not one or the other, it's both. So, gravity involves negative energy, unlike all the gauge theories, which involve positive energy. So I think it's quantum, but why can't it be the non-local part? So if you take any of the gauge theories, the local is the real manifestation, and the vacuum is the fictitious or virtual bit. In gravity, let's suppose that the vacuum or non-local bit is the real one, and the local aspect is the fictitious or virtual bit. It's just reversed. Got the same two bits, but in reverse. Which would be entirely in accord with that, and in other symmetries. In this case, the local aspect is going to be inertia. The relationship between gravity and inertia has never been properly established. That would be the fictitious or virtual force, in which we now know it is. Since inertia is repulsive rather than attractive, its quantized manifestation will be spin 1. We immediately solve the non-renormalizability, because the local manifestation is the same as the other gauge ones, except that this one's virtual. And I say, if quantum gravity in the conventional sense were true, then there wouldn't be any continuous vacuum. Because the only thing that could be continuous to give you the vacuum would be quantized locally. So it's no good. So paradoxically, in my view, quantum gravity can't be true quantum field, because it excludes vacuum. But Newtonian gravity could. It could be the non-local part of the quantum theory. Now, let me just talk about classical physics and quantum physics. And the general view is that there's a classical regime, there's a quantum regime, and there's some boundary between them. I think it's completely wrong, this. There's no such thing as classical physics at all. There's only quantum physics. There's only quantum and relativistic physics. Classical physics is a movable feast. You can call any approximation you want classical. What you're simply doing is a multiplicity of ways of deriving explanations using a minimum number of assumptions. That's the virtue of classical. It's not that it's something completely different from quantum, it's just a convenient way of doing lots of things without having to go through all the bother of doing all the quantum calculations. And if classical physics ever confronts a new issue, it just invents a new category, which it subsumes under the classical label. So Maxwell's equations incorporated all of the electricity, magnetism and optics, one theory, but it surreptitiously introduced special relativity or equivalent. And it wasn't for a long time that was resolved. But even more disruptive were discrete charges. There was a hint of them in electrolysis studies in the early 19th century, but late in the 19th century it became clear that there had to be discrete particles with charges. Now Maxwell had avoided those, but once we assume them, then you get a wholly different perspective. You open a completely new kind of world. But classical physics simply says, okay, let's now, we didn't have discrete charges before, but now we'll introduce them. No problem. It changes itself to introduce them. So there isn't any fixed thing called classical physics. But the problem is, discrete charges really involve quantization in a surreptitious way. In a trivial way, you can show it. You can show that energy, electrostatic energy, if you're transferring information at speed of light, if you've got relativity as well, then this is 1 over time, basically proportional to frequency. Simply discretization of charge plus relativity forces you to go down the quantum route. And we also talk about classical thermodynamics, as though it really is classical. And it puzzles people because it's a separate subject on its own. It doesn't have any connection with lots of other parts of physics. But the very basis, heat, isn't really classical at all. It's got all the signs of being quantum mechanical. So we've got a random motion that really isn't a real true part of classical theory, but we disguise it as a lack of knowledge rather than something fundamental. But if we subsume heat under a single unanalyzed category, type of energy, we can just incorporate it totally into classical physics, and then we can carry on doing classical physics with it. And it looks classical. And surely the second law of thermodynamics is not a classical concept at all, it's clearly quantum mechanical. But even when quantum mechanics produces new results, we can repackage them as classical if we just make a few tweaks. I mean, quantum mechanics, quantum results, lots of them have been reimagined using what's called stochastic electrodynamics. You have a Maxwellian theory with a background field. And once you assume the background field, then you can do everything that you can do in quantum mechanics. And it's a purely classical way of doing it. It's not classical, but it's a classical way of doing it. So there is a quantum element, but you introduce it in a way that produces minimal non-classical elements. So you just refine classical to introduce something extra. So there isn't any classical physics. Lots of more examples. A colleague of mine is actually introducing, well, he's quite successfully generated a Higgs mechanism from a scalar field, which he added to Maxwell's electromagnetic theory. So he's wanted to do that, and he's done that. And you produced a version of the Dirac equation. This is something I was talking about when Lou was talking yesterday. We're using Lou's discrete version of differentiation, which can be interpreted as either classical or quantum. And I'll very quickly show you that, because this is the... I'm actually going to... The reason why I'm going to use partial df by dt instead of full is because I'm not going to use a velocity operator. Okay, so...
Notice that we're halfway to quantum here because all derivatives are represented by commutators.
Yeah, that's right. It is discretized.
Yeah.
But you can do it in a sort of semi-classical way.
That's right.
So I can represent a wave function like that, similar to the way I would do it normally, except there's no phase term. And an operator like that, with these representing these differentials. When we do a bit of algebraic math manipulation, we get this, and which boils down to this. And if I do the four signs as I do in the Dirac equation, I can get this into this equals 0. Now the key thing I want you to look at is this. Because there's no mass term in it. Because you commutators, the mass term goes. And it doesn't require the I or the IH bar term, which you normally have to apply in a sort of ad hoc way. If you look at that, you can put an IH bar there if you want, or you can leave it out. It's not going to make any difference to the fact that it's 0 on the other side.
So Peter, just how did the mass term disappear? Can you just run that?
It's because it's a scalar quantity, and when you do a commutator of it, it just disappears. The scale will just disappear. Okay, it's very easy to show. You can't really do a commutator of a scalar.
Yeah.
Yeah, it's got to be, something else. Yeah.
Right. I guess I don't see what's sort of happening physically, but go ahead.
Well, I don't know what's happening physically, to be honest, but I do know that mathematically it works perfectly.
Okay.
Now, so, in effect, you can use the equation either as a classical one, or a semi-classical one at least, or a quantum one. Because you can put IH bar in front, or you can leave it out, as you please. But also, from what we were talking about yesterday, if I look back at this, and only look at the operator, and in the nilpotent theory, I define any term by its operator, a creation operator by that operator. Now, if I define it by that operator, then you can see that that is the same as its reverse. If I change the signs, it doesn't change. It doesn't change its function. So I think that may be a route into doing something over this Majorana business. It's worth looking at. And you get similar things in relativity. Practically everybody thinks E equals mc squared is relativistic. Not at all. Einstein tried to derive it by relativity and failed. He had to introduce it as a constant of integration, which could be anything. It doesn't have any reason in relativity. Delta mc squared has a reason, but not mc squared. Not the total energy. Special relativity cannot derive it. And so Einstein does his equations so they match classical ones. So he's matching it with classical energy conservation. So the only source of that term is a classical one. And I found a whole series of 17th, 18th and 19th centuries calculations showing mc squared is sometimes as a disguised potential energy term in the particular case of light photons, which is totally classical. And the calculation of light bending is another one. So how subtly the connection with classical physics and with seemingly more advanced ones. And this is the standard method, curvature of space and all that. But let's look at that again. We're told we need the full field equations with curvature. But it said that Newton proposed a classical one which could be calculated by this potential energy equation. It's a hyperbolic orbit, so that there's a huge eccentricity. And you can calculate 2 over E, which is double the bending in and out, so that gives you 2gm over c squared r for your deflection. However, the real deflection is 4gm over c squared r. We believe. Well, let's just suppose it is. But we don't need general relativity to do that. It's been shown by several authors that you can do it using special relativity because you just introduce length contraction as well as the time dilation, which was the 2gm over c squared r equivalent. However, more interestingly than that, you can do it by a purely classical equation. Because this is just as much a classical equation as that one. Except that this is the kinetic energy equation. And I think the 2 18th century authors who looked at this may have had this in mind because they both started from the black hole equation, which is the kinetic energy equation. And this is simply the equation of an object brought into orbit. It's not an existing equation. But it's very subtle, this. We need something outside of classical physics. If we think of the velocity of light not as a dynamical velocity, which it isn't, because the photon is not a material particle, it's a particle travelling at the speed of light, which only has mass energy, it doesn't have any invariant mass, then light always travels at this velocity. But this velocity doesn't have any dynamic meaning unless there's a force acting. And so it only becomes dynamic when it connects with a real force. So this is what it is, it's pulling it into orbit. So you're kind of using special relativity in a very subtle way there. But it can be made totally classical. And I'm interested in the word Newtonian, because I think there are 2 different words. There's with a small n and a big N. And the word Newtonian with a small n, the physics of identifiable particles determine positions interacting with each other in identifiable ways with identifiable outcomes. That's Newtonian. And if you look at the Principia, there's a lot of that in the Principia. But this is different from Newtonian, which refers to statements made by Newton himself. Now, I wouldn't have written 3 books on Newton if this was the only thing that he wrote about. I'm much more interested, personally, in this version, because these often diverge widely and are not Newtonian with a small n at all. Strict development from assumed invariable principles, Newtonian with a small n, produces an entirely different style of work from inductive search for explanations of seemingly anomalous experimental results.
There was also a thing that in England, Newtonian physics was what Newton was talking about.
Oh, but only some of Newton.
Yeah.
Because there's other parts of Newton which are nothing like that.
Yeah, but what was being taught as Newtonian physics
Oh yes, that's correct.
was what Newton was talking about. But in the continent of Europe, when they were talking about Newtonian physics, they were talking about Boskovich's theory.
Okay, but let's just talk about Newton for the moment.
Okay.
I say the reason why this is important is because there's an innate assumption that this is the way to do physics, Newtonian with a small n, or similar, which is a deductive sequence from accepted principles. And Newton himself provides a striking illustration of how this isn't how to do physics. If he's presented with intractable data, as he often is, he doesn't resort to small n Newtonian models. He doesn't say, where can I do a model using my Newtonian laws? He tries to establish abstract generalizations, minimalizing assumptions and maximal explanation. That's what he tries to do. And he's very good at it. At least as good as he is at Newtonian with small n. And I've looked at his reasoning in this style, and it shows us many of the directions in which physics would go. You can see from his reasoning why you get the developments of electromagnetic theory, quantum theory, relativity, thermodynamics, modern ideas of the structure of matter in the way they did, because of the way he reasons. And the reason why this is significant to us is because this is how we should proceed now. Because we've got equally intractable data, not in the model building Newtonian with a small n. I don't know if I've got much time to talk about general relativity, so I'll say a little. General relativity is a problem, not because it predicts wrong results or because the equations are untrue. Not so. It's because it forces us into a particular mode of reasoning which a particular individual used at a particular time in particular circumstances which no longer apply. Because he was trying to get a unified field theory. We don't really believe that what he tried to do there was going to work. This has become set in stone again as the only way of proceeding, even though it's no other physics looks like it. So people say general relativity, then this applies to what was said earlier, by Mark and so on. General relativity is due to the curvature of space-time. Well, that's not true at all. It's just one model, it's just one metaphor. It isn't due to it at all. So, the concept of four-dimensional space-time as a physical object is completely refuted by relativistic quantum mechanics. This is the object, and even if you don't use my nilpotent structures, it still must look something like that. And this is the space and time version with proper time. But notice that it's not this, which is four-dimensional space-time, it's that, which is a more complicated structure. Again, it's not like that, it's like, that's what four-dimensional space-time is, well, that's what we get. It's not such a thing, and we've got proofs that it isn't correct, because we have wave-particle duality. Because that isn't correct. Because we try to bundle everything into a physical picture, we get this duality. And the non-observability of time in quantum mechanics shows that you can't push time as a version of space. Curvature of a mathematical construct is certainly possible, but it doesn't quite have the same cachet and physical significance of real space-time. It's not a single physical entity at all. We can use this metaphor if we want, but there's no ontological significance to it. the concept of gravitational forces is valid, and you can do a field interpretation of general relativity. We saw one in Moscow when we were there from a couple of Russian physicists, which was a perfectly good way of doing it. I'm going to say a few things with regard to Newtonian gravity. Newton always avoided any particular explanation. He didn't even say it was a force. Force to him was an effect, not a cause. Curvature is one way of achieving the effect, but it's no more or less valid than any other. Cartan, in fact, showed that you could represent Newtonian gravity by curvature, just as you could Einsteinian equations. And in fact, I found Newton used the curvature method himself in Proposition 44, Corollary 6 of Book 1, when he was talking about revolving orbits. He actually used curvature method, amazingly, including something that's equivalent to a geodesic. And best of all, the universe just isn't curved. It's just proved that it's as flat as Newton himself thought it, and Euclid. It is not curved. And I say the curvature methods forced physics into a cul-de-sac, separating gravity from the other forces. Now the justification is that all the experimental tests are correct, but none of those tests required all of that. But I don't think it's the equations that have the problem. I'm not worried about them. I can use them. I'm not worried about them. It's the way they create a physical interpretation. And the standard physical interpretation they've created is that there's also this self-interaction. Gravity produces curvature, curvature produces more gravity, which produces more curvature, which produces more gravity, and then eventually it spins out of control. But experimental testing has shown that the equations don't destruct in strong fields. We've had strong pulsars and we've had gravitational waves and so on, and they don't destruct. And I say, I'd like to say this if I can, the wrong interpretation of the magnetic component, the relativistic bit of gravity, has been put forward. And this is where ontology and epistemology comes in, because I think they've gone for an ontological explanation, not an epistemological one, and that's where they've gone wrong. If we define inertia as a fictitious force, then we don't have any special status in the universe for the Earth. And again, it would solve all that problem that I mentioned earlier. And if you had a Machian origin of inertia, I did this in the 1970s, you get this equation, and you get this acceleration term in the redshift. You get the redshift derives from that acceleration, and it's equivalent to dark energy of 67%. We now know it's 68, so that's pretty good. So, Newton has something useful to say here. He describes mass as vis inertia, force of inertia, because he thinks it's a kind of force opposing the real ones. It's not a real force, it's a fictitious one. And he also, in an unpublished Proposition 43, which is intended to be a conclusion to the whole book, he says, if the Earth could be imagined as a taconic, at the centre of a taconic system, with all the sun going around it with all its planets and go around the Earth, we can't prove it isn't, because there could be a force coming from outside, an inertial force, which completely countered the gravity. Now, of course, we perceive the Earth as the centre of the universe because we have a fictitious inertial force. But a real one would exist only if the Earth were the centre of the universe. So if we going to take the Earth as not as special, then we must assume it's fictitious. So perhaps that's telling us the interpretation of general relativity that will give us the maximum consistency. And it would even be good for general relativity because it wouldn't destruct in strong fields. Okay, these are just a few other observations. I've got a couple of minutes maybe?
Yeah, not more than 5.
No, it won't be more than 5. I've shown that supersymmetry without extra particles, and in fact this review has recently been published and it discusses my argument in it. Right, no extra particles, this review here.
independently.
Yeah, it's well, it mentioned it refers to my
You
book.
didn't know him before.
No, I knew with these people. This is in Zeitfrisch, Zeitschrift für Naturforschung. Yeah, Zeitfrisch, this one. So, they think that's a plausible argument. I've also often said that the symmetry, that group symmetry, preserves the proton regardless of any decay. And I've got something to say about renormalization, but I'm not going to discuss that. I'll leave that. Okay?
If you take a discrete point of view, then curvature is just identical to the non-commuting of various derivatives.
Oh yes, I understand that. Yeah.
And then that fits with gauge theory and
Yeah,
general
okay.
relativity. But
Sure.
what we haven't figured out is how to get general relativity into that discrete
Well,
framework in a way that looks, it's almost there, but it's, you know.
I know I've seen that argument presented at ANPA in previous ANPAs. That the argument.
Yes.
Yeah, and I'm interested in the argument. Yeah, but curvature is simply another way of doing covariant derivative.
Yeah, that's what I'm saying.
You've got a covariant derivative, so in other words, you've got d by dx on d by dt, and you just add field terms on. Or you can add curvature
And in the
terms.
discrete world, most of the derivatives are non-commuting with one another. It's just full of curvature. But it's very hard to get things to flatten out, so different world.
Sorry, but I'll answer that over there first.
Well,
Yeah.
shall I go?
Yeah. You go first.
It's 2 points in the first part of your talk. The first one against errors. You were proving that some of these assumptions were
Yeah.
false,
Yeah.
starting from your formalism.
Yeah.
So my question is, these assumptions which are shown to be false,
Yes.
were they just
Well, it's because of ignorance. They don't actually know what the answer
no,
is.
I wanted to ask whether they were consequences of the use of a different formalism.
No,
it's
they're just arbitrary assumptions.
it just well, okay. The second point, it was referring to that duality between vacuum and one being virtual
Yeah.
and the other being
Yes.
real.
Yeah, real and local, virtual and non-local. Or the other one around.
This is a very interesting consequences. But could you identify one point of view as objective and the other as epistemological or not?
It's possible. It's possible, but I think it's more that we. I don't think you can reverse the locality of gauge interactions, but you can reverse the locality of gravity to say that that point of view, seemingly good, isn't good. I don't know. I don't think it's just an arbitrary point of view. Though I do agree with some of the things you said about different points of view, epistemology and ontology, and in that group structure of mine there's epistemology on one side and ontology on the other, and they're both part of the system. Neither is completely true.
Okay, thanks.
So yeah, you go back a long way to when you were talking about relativistic mass.
Yeah.
I've been talking to a lot of the people about things like this, but and it seems to be they're redefining certain physical terms. I got diverted because they seem to redefine Newton's force equation from what I was taught at school. But on the relativistic mass thing, why they've changed that, I think one of the reasons they're giving, what I haven't fully checked, is that Einstein didn't use relativistic mass and it was people who came after him who used relativistic mass.
Yes.
So their sort of like justification for getting rid of it is because Einstein wasn't really using it.
Well, Einstein didn't use Minkowski space-time,
Yeah.
but everybody after him does.
Yeah, but Einstein did accept Minkowski space
He did accept it. Yeah.
in the end, but it's the relativistic mass I think the excuse they're trying to give is
Yeah, okay.
Einstein wasn't
That's
using
very
it.
interesting, that, yeah.
And so that's why they're redefining a lot of physical
But they're doing it
terms.
in a bad way because
Yeah.
relativistic mass is the only good definition.
Yeah, the way
The
I
other ones no good.
the way I understand things is from relativistic mass, but then they're redefining lots of equations.
Newton's work on refraction of light
Yeah,
actually uses relativistic mass, though he doesn't know what it is.
yeah,
It
probably.
actually uses relativistic mass for the light particle, but he doesn't know what it is. You look at his equations, that they're equivalent to relativistic mass.
But it's getting really confusing because they're redefining terms.
But it's completely wrong to do that,
Yeah,
especially if they're inferior versions.
yeah. Okay.
Just a very quick comment. What you said about the way Newton thinks,
Yes,
and probably the way you think too,
Yes.
is a person would call that an abduction.
okay, I've heard the
And-
term, yes.
And I think that's very important, particularly you then have to look at the structure of our institutions of science
Yes,
and the extent to which they support or actually make abduction particularly difficult.
yes. It is very difficult. It's very difficult for anybody to accept that it's a perfectly valid way. In fact, it's the only valid way. In
It's
many
a
cases.
very, very serious problem.
What is abduction?
Abduction is
I
where you
think so.
speculate on possible causes for a phenomenon rather than necessarily deduce or induce from observation.
Your promotion matrix doesn't allow it from
No.
What do you think about dark matter?
Dark matter, I think, is probably dynamics. I don't believe there's any matter at all.
So,
And I know that dark energy is definitely
No,
dynamics.
dark energy is nothing. It is not problem. Dark matter from the gravitation, but dark matter.
I don't believe there is any.
It's
I don't believe there's any dark matter.
sort of, this abduction thing, would that be,
That's my personal.
would the abduction thing, is that related to what Einstein seems to do? He seems to go from a thought experiment and then applies it to physical
Most
reality.
great scientists do this.
That's what they're doing.
Most great scientists.
If-
Most teachers of science, particularly in school, don't do this.
yeah, and I think people like some experimental physicist Essen says, no, that's the wrong way of doing it.
Louis S.
Louis Essen says that's the wrong way. But it's sort of like they've sort of had a dream
Yeah.
and that's how they decided to fit
It's a creative
measurements
process.
to.
Yeah, you can't describe it. And if you can't do it,
Yeah.
then you're going to be against it. Not everybody can do it.
There's a problem with Einstein's thought experiments. He imagined what would it be like to travel at the speed of light, and sort of that's not an experiment you can actually do.
A thought experiment.
Yeah, thought experiment, and then works back from that.
Anyway, Peter,
Okay.
thank you very much. It's actually at 8 o'clock.
This is a review of a book of mine. If anybody wants to have a copy, they're there.
can we leave stuff here?
Yes, I'm going to remain here because I've got some work to do. I've got the next 2 hours. This is one of our things.
Yeah, you got it.
That's great. I don't
You want
know.
more? Anybody else?
All the stuff.
We start in the
I think if I was over there, I might have got it. Oh, that's it. Thank you.
Yes, of course.
Anybody else not got one? Have you got?